Before I get started, I don't want to forget to acknowledge the collaborators that I have the pleasure to work with on these projects. I will talk about two compounds. I'll briefly touch upon some older results on chromium triiodide, which is a material you obtained from Alberto Morpurgo in Geneva. But then the bulk part of the new results I'll show today is on chromium sulfur bromide. Who would have guessed after the last 3 talks? And I'll talk about samples we obtained from Xavier Roy and Corey Dean in Colombia, and we also collaborate very closely with a group of Alex Högele here at the LMU. All right, so I guess at this conference, and especially after these exciting talks before me, I don't have to spend too much time motivating why we're interested in two-dimensional materials to begin with, and two-dimensional magnets in particular. Here, I still want to just highlight, the beauty of these 2D magnets in part lies in the fact that many of them constitute near perfect realizations of various spin lattice models. And we have a big degree of freedom in choosing the type of spin models we'd like to implement between possibly not so interesting Ising models to XY models, all the way to 3-dimensional Heisenberg systems on various lattices. And on top of them, that we have this exciting opportunity of tunability of 2D magnets, be it by gating, by lights, proximity, moire, what have you. And these opportunities brought a lot of excitement, not only in the field of van der Waals heterostructures and van der Waals physics, but really also in the fields of magnetism and spintronics, where I believe that there are true novel opportunities to look at new functionalities and new physics if magnetism in reduced dimensions. And one such result I hope to show you in my talk. Now, looking back, it was said before, one of the first compounds that was isolated of the atomically thin van der Waals magnets was chromium triiodide. And this material, as well as many, many others, have been studied predominantly using this optical technique called magneto-optical Kerr effect, in short, MOKE, which is a polarization-sensitive optical microscopy, which for a long time was actually the only way to address these magnets in real space. And it was, of course, instrumental in the development of this field. Here you see one of the very early results of a MOKE hysteresis curve, and here the case of a chromium triiodide flake in a two-domain state. You see right away here how MOKE, while again having been instrumental in this field, has also its limitations. The first obvious one is on the spatial resolution, which is in the micron range, but it's also largely a non-quantitative tool and one that is just intrinsically not applicable to all materials. So there is a need for more advanced instrumentation and imaging technologies to bring this field of van der Waals magnetism further. And this is where this technology of scanning single spin microscopy comes into the game. And I should, before introducing that, mention that there are notable exceptions, and in particular in recent years, there have been really exciting advances in using magnetic force microscopy and also scanning squid microscopy in this field. But for the moment, as far as I know, at least, these are still niche cases. All right, so the approach that we're pursuing is to use essentially a single electron spin here in a scanning probe configuration to bring that spin in close proximity to a sample of interest and then probe magnetic stray fields by performing optically detected electron spin resonance. I want to focus my talk mostly on the 2D magnetism case, so I'll be very brief on this part, but we can talk more about it later. So here is a sequence of such optically detected magnetic resonance, in short ODMR spectra, and you see right away how those resonance dips, which essentially corresponds to driving this spin resonantly and reading this out all optically, how they split up linearly with magnetic field along the NV quantization direction, the spin quantization direction. And this is the basic principle of the experiments we're doing. There are a lot of refinements, which I will not discuss today, but taking all things together, this type of magnetic imaging technique really is a, I would say, rather powerful complement to the tool set of experiments that we have around in the field. It brings excellent sensitivities down to a level of single electron spins. It has nanoscale spatial resolution, which is uniquely determined by the standoff distance between this spin and the underlying sample. It's quantitative, and I'll come back to that later in my talk. It's also largely non-invasive, and it can extend into a rather large dynamical range up to the gigahertz frequency range. So how do we do all of that? So there's still a bit of technology here. And I should say that this is a technology that was originally developed in the group of Amir Yacobi, whom you've heard speaking this morning. What we're doing is to fabricate these scanning probes out of single crystalline diamond. The spins are sitting here at the very apex. And then we fix this using some holding structure to a quartz tuning fork, which is our force sensor that we use for tip distance, tip sample distance control. Since this was originally shown in this paper here, we pushed the technology further. In particular, with my group, we focus on the photonic properties of these tips. These are not only AFM tips, they're also photonic nanostructures. Here is the latest generation of our devices. These are essentially nanoscale parabolic reflectors. They allow for something like 12% collection efficiencies from the spin that's emitting photons to the detector that's doing the data acquisition, and with that we get sensitivities on the order of 500 nanotesla per square root of hertz or so. So these are by now not so new results anymore. I now want to show a rather recent technological achievement from the group, and that concerns the way how we drive these spins for magnetometry. Traditionally, we, and I would say everybody in the field, has been using something, I would say, of modest engineering, simply bringing in some wire, typically bonding wires nearby the spin, either with some positioners or bonded over samples. And that's, of course, a very limited approach. It's rather flaky. This moves over time. It takes real estate and oftentimes limits the field of view where you can operate the scanning NV magnetometer. So for this reason, many people before us have thought about the problem of how to address that and make something more integrated. And here I show you, to my knowledge, the first result that shown this, where the group, again, of Amir Yacobi has placed such a scanning probe here onto a commercial cantilever and put the bonding wire instead of the sample here onto the scanning probe. And that, of course, is already some nice way of integrating that. We've tried this ourselves, but found that also here these wires move, so the driving is not so efficient. It's also highly tedious to align these structures. So we wanted to overcome this issue, and to cut a long story short, this is what we came up with. In our newest devices, we integrate these microwave delivery lines actually on these holding structures. What you see rendered in 3D here is a 3D printed glass structure that we print with these overhangs so that we can just evaporate some gold without any lithography. We automatically get these microwave delivery lines here. A real device looks like that. That's a false color-coded SCM image with the tuning fork, this 3D printed holder, and the leads that you see here. And typically we just glue our diamond device now here from the bottom. And the result is that we are very close to these driving lines. We can very efficiently drive the spins, and this is a much, much more robust approach to what we have ever seen in our labs before. So here's one of the figures of merit. We can drive this spin rather efficiently. This is a case where we have something like, in excess of 10 megahertz Rabi frequencies, so spin flip times of less than 100 nanoseconds. We do this in a cryostat without any appreciable heating. We're still working out how much the actual power benefit, so to say, is compared to the existing approach. All right, so back to applications. Using this scanning NV magnetometry technology that we have available now for almost 10 years, we addressed a range of physical systems over the years, and I'm not going through all of them. I just want to highlight, before going to the 2D magnets, that one particularly productive field, and this was opened by the next speaker, Vincent Jacques, is to apply this technique to studying multiferroics, such as here in the case of BFO, or antiferromagnets. This is then the focus in my group, here in the case of chromium oxide. But again, today the focus is those 2D magnets. And here I want to first highlight our earliest results in this field, which were motivated, as I did in the beginning of this talk. And what we obtained here from Alberto was just a range of such flakes of chromium triiodide. You see them here photographed before encapsulation. I should stress again that these chromium trihalides, they are really extremely fragile objects. One needs to encapsulate them to make them air stable, and even then, as we've seen in one of the prior talks, they degrade over time. Nevertheless, we were able to put them into our cryostat, and here you see a stray field map obtained on exactly this region. You see that the tri-layer generates a stray field, the bilayer does not. That's because of this antiferromagnetic intralayer exchange interaction that Stuart Parkin referred to. And what we can also do on these data, because oftentimes people don't care so much about stray field, but more about the magnetization, is to reverse propagate this measured data to the underlying magnetization. This by itself is a rather, I mean, I could talk about this at length. I just give you the result here, which is here this magnetization map over this region here, where we get now magnetization in quantitative units. And we carried on, did the same thing with monolayers, 5 layers, and so on. And this is why I want to stop discussing these results. You can read this up yourselves. The main message was that we could actually elaborate on this antiferromagnetic intralayer coupling, which is unexpected. And with our work, we were able to show that this was actually due to a suppressed structural phase transition in these encapsulated samples. All right, so these results and this demonstration that we can use NV magnetometry for nanoscale imaging of van der Waals magnets really motivated us in my group to dive deeper into this field and to explore various directions. And I think many of us in this room work in different directions. I think first and foremost, we're trying to engineer non-trivial spin textures such as skyrmions that we've heard about before by proximatizing these magnets, for instance, with heavy metal containing substrates. We're also interested in domain walls and dynamics of domain walls. Here is a proposal from Jovan Kim from some 10 years ago that showed that we can actually use domain walls, this is a theory proposal, domain walls as waveguides for spin waves. And we believe that these van der Waals magnets would be ideal platforms to actually realize and demonstrate that. However, to go in these directions, one obviously needs more complex structures, heterostructures, and ultimately some people may want to scale this into an actual technology. And here you see the strong shortcoming of these chromium trihalide platform that I've shown before. This is the best monolayer we were ever able to isolate after weeks of searching, and you see even that is rather small and strongly disordered. And here comes now this new wonder compound into play that we've heard about a couple of times already, chromium sulfur bromide, that essentially solves all these issues of structural instabilities. I think the beautiful physical properties of chromium sulfur bromide, they were already highlighted in the previous talk, so I'm not going into them again. But I do want to stress that, exfoliating these crystals immediately gives you huge flakes here on the order on excess of 50 microns across that are perfectly air stable. So we don't encapsulate our samples, we just leave them standing around, and even after weeks in atmosphere, they retain their pristine magnetic properties. What we did first was just to look at fundamental properties of such exfoliated flakes. Here you see a case of an arrangement of various layers. You see again bare stray field, and we can transform this into the underlying magnetization, which in this case is in plane, the net magnetization, and the spin arrangements that we infer are shown here. If you want to know more details about this more systematic materials characterization we've done, this is on the archive now. Maybe one highlight is that we were also able to quantify the magnetocrystalline anisotropy down to the monolayer limit and look at its temperature dependence as we went across the nail temperature. But instead of, again, presenting this, I now want to spend my last, I guess, 2 or 3 minutes or so showing you some brand new results that build on these pristine properties of chromium sulfur bromide, and that, at least as far as I know and understand, really represent a completely novel way of controlling magnetism on a nanoscale and controllably inducing domains or domain walls by something that we like to call lateral exchange bias. And let me explain to you what I mean by that. So let me first present the sample that we looked at here. This is again an arrangement of various layers. The important layer is going to be this bilayer here and its adjacent trilayer, as well as this bulk piece of junk up there that's going to be important. So if I take this line cut highlighted in blue, you get this simplified picture of the trilayer that is atomically connected as a single crystal to the bilayer, the way I show you here, and then somehow connected, and this is just symbolic, to the bulk up there. And we're going to focus on the properties of the bilayer in this region here, which I show you here in an image just taken roughly at zero magnetic field, where you see that the trilayer, and there's also monolayer here, they show a net magnetization, bilayer practically unmagnetized. This is just a little artifact here on the edge. Now the important or the interesting thing is how we can get into that phase where this bilayer is antimagnetically ordered if we start in a fully polarized state where we have applied a strong magnetic field along the easy axis of chromium sulfur bromide. So let me first show you, just walk you through these cartoons. We start in this state here, then we reduce the magnetic field, and it turns out this saturation field is strongly layer dependent. That's something that has been established before. So the trilayer becomes antiferromagnetic before the bilayer does, and then we reduce the field further, and at some point, a antiferromagnetic nucleus will nucleate in the bilayer. And this is bound to nucleate at the interface to the adjacent trilayer in that case. And the reason is simply that here, next to the magnetic stimulus that drives the bilayer into the antiferromagnetic phase, there's also the exchange stimulus because of this nearby trilayer. So the domains always start to grow out here, and then they become bigger and merge in the end. And here I show you an animation, and this was done on a different flake. I come back to that flake later, just to show you how we can actually map out this phase coexistence between ferromagnetic and antiferromagnetic phases, and how this really propagates as a rather smooth domain wall or phase boundary through the sample. I should say this phase coexistence per se is not something overly surprising, given that this so-called spin-flip transition that we look at here is of first-order nature, and therefore you expect such phase coexistence. All right, back to our favorite flake over here. This is now a snapshot when we're in this state of coexisting phases. Oh, sorry, my arrows moved around, but this should be the ferromagnetic phase, antiferromagnetic phase, as I just explained, and we can just also image the whole thing here, where everything is saturated. So far, so good, and maybe not so interesting yet, depending on your angle. Let us now go to the case where we do the same experiment, but we approach the system from negative magnetic field. So we just flip the magnetic field. So what happens there is, again, we saturate the layers, and this is just highlighting what I showed you before, namely that the saturation field depends on the number of layers. So we can selectively saturate one of the flake parts after the other. So first we saturate everything, then we reduce the magnetic field. First, the trilayer goes into antiferromagnetic phase, bilayer stays ferromagnetic, and the important thing is that the bulk part stays untouched, because here the saturation field is so large that we never change the spin configuration within the fields that are available to our experiment. So now what happens? Again, antiferromagnetic phase nucleates at these boundaries because of this exchange bias or exchange stimulus. But the important thing is that we now switched the arrangement of the trilayer as compared to the previous case. So now, instead of having, upper layer left, lower layer right, as we had before throughout, we have the opposite arrangement on this left side here. And then, of course, these things will merge, and you would expect the domain wall to occur. And indeed, that's exactly what we observe. So this is, again, an NV magnetometry image. You see here the rest of this ferromagnetic pocket, and here this antiferromagnetic domain wall that we were able to create in a highly controlled way. This is an extremely reproducible experiment, works every time we want to do it, or rather, every time my postdoc Clément wants to do it, he sits back in the audience and you can talk to him afterwards. Okay, let me just, okay, this is just for completeness. Turns out these images, we reverted the field, but this is for technical reasons. Let me just wrap up. Here is the difference of these two cases of this ferromagnetic pocket, then with or without domain wall, created in the way I just told you. And now we're coming to very preliminary things, namely, what can we do building on that? And we believe that there's actually a lot to be learned from these kind of images. There's a lot of intrinsic physics of this chromium sulfur bromide compound in it. Let me just flash two things. One is this ferromagnetic pocket here has a rather peculiar shape. Here is a more highly resolved image of it. You get this cusp and these kind of curvatures on the phase boundaries. We believe that one can understand them intuitively. We haven't gotten the theory fully right yet. In the following way, it's just a matter of minimizing boundary energies. You have here this antimagnetic domain wall where you have exchange penalties that you pay on both layers of your bilayer. Whereas here, you have the phase boundary where you pay this exchange penalty only once. Thus, the energy per length of this phase boundary is approximately half of the energy per length of this antimagnetic domain wall, and the same applies here. So the system tries to minimize energy, and it does that by having this phase boundary protrude into the antimagnetic phase and make this cusp shape. Okay, and similarly, and now I'm really almost over time, we're trying to understand this, the internal structure of this antimagnetic domain wall in more details. Why does it create this stray magnetic field? We have some simplified model at this point, which we can talk about if you ask me later, but we are still seeking more thorough, in-depth theory understanding, and if any of you have insights, please come see me afterwards. So with that, I'm at the end. To summarize, I presented briefly this technique of scanning NV magnetometry, our newest technological invention of this integrated microwave delivery, on-tip integrated microwave delivery, highly efficient, compact, and powerful, and then this new concept of what we termed for now the lateral exchange bias. I'm happy to hear your critical remarks on this name. And an outlook is, I mean, we have various ideas in mind, but in particular, spin waves in van der Waals magnets are a big focus in the future. So with that, I'm at the end. Thank you very much for your attention, and this is a rather old but still valid picture of my group. Some people are missing, sorry for that. Thanks. And we have positions. Let's
take just one question.
Thank you for the nice talk, very nice results. I was just wondering, so you don't see any signs in the tri-layer of that mixed state that we saw in our joint work?
No. Okay, this is now almost an insider discussion, but yeah, it's a good question. Maybe I can try to paraphrase it. The question is whether we see a state where the tri-layer is not, say, left, right, left, but left, left, right. And these are states that have been seen by this beautiful work from Frazane in Alex's group by optical spectroscopy, but as you know, they occur in a very narrow range in magnetic field, that's one problem we have, and a magnetic field that is currently inaccessible for us for imaging. We can go to that field, but we can't image at that field for reasons which we can discuss afterwards.
So what's your magnetic field resolution when you...
Well, whatever the other cube magnet allows us to do. So I don't know.
Thank you.
I mean, nominally, I mean, we have steps of less than a Gauss, but whether this is then the precision, I don't know. But that's not the limitation. The limitation is somewhere else.
Okay, thanks.